Hello again, welcome back to another lesson in geometry. Today we're covering section 12-2, chords and arcs. So we've seen arcs, remember minor arcs and major arcs before, but nothing about chords yet. All right, so complete the converse of each statement. So converse takes us back to our logic unit. Remember, if we had a hypothesis implies a conclusion, the converse would say the conclusion would also imply the hypothesis. Okay? So if I'm happy, then I sing. So to flip that around is if I sing, then I am happy. So that's the one we would circle. Okay. If parallel lines are cut by a transversal, then the alternate interior angles are congruent. If I want to flip this around, I still need some lines to be cut by the transversal so that alternate interior angles are congruent, and then we could say the lines are parallel. So if lines are cut by a transversal are not parallel, that's not what this is asking. If lines cut by a transversal form alternate interior angles that are congruent, then the lines are not parallel. That's not what this is saying. If lines cut by a transversal form alternate interior angles that are congruent, then the lines are parallel. That would be the converse. Okay. All right, a vocabulary builder, chord. A chord is a segment whose endpoints are on a circle. So this is a chord, RS. Its endpoints are on the circle. Related words are the arc. Remember, our arc is going to be found by this way around. Okay, so instead of going across the circle, around the circle from one point to another. Okay, so complete each statement with always, sometimes, or never. A chord is sometimes a diameter. So the diameter is a special chord that goes through the center. So a diameter is always a chord. A radius is never going to be a chord, though it doesn't touch the outside of the circle twice. A chord always has a related arc. Okay. And an arc is sometimes a semicircle. So sometimes an arc will be halfway around the circle. So here is another chord that's also a diameter. And this arc would be a semicircle for that related chord. All right, let's flip it over and look at page 2. Okay, we have 3 theorems here about central angles and their related chords and their related arcs. All right, so first theorem, within a circle or in the congruent circles, congruent central angles have congruent arcs. So in this circle over here, blue angle here is central angle is congruent to the red central angle. And they're going to have the same arcs. So this blue arc is going to have the same measure as this red arc. All right, so if angle AOB is congruent to angle COD, then arc AB is congruent to arc CD. The arcs will have the same measure too. Now the converse of this is also true. So if the arcs are the same, then the central angles will also be the same. Now remember, a central angle always needs to have the center of the circle as the middle point in your angle. All right, theorem 12-5, within a circle or in congruent circles, congruent central angles have congruent chords. So same thing as before. We have this central angle here and this central angle here, and they're congruent to each other. And then we have their related chords, not related arcs this time, and the length of their related chords should also be congruent to each other. So this blue chord should be congruent to this red chord. So if the central angles are congruent, AOB and COD, then the chords are congruent. So AB is going to be congruent to CD. Our converse would say if the chords are the same, then the angles are the same. So since AB is congruent to CD, those are the 2 chords, then the central angles that are related to those, angle AOB, will be congruent to angle COD. All right, and then our last theorem says, within a circle or in congruent circles, congruent chords have congruent arcs. So if the chords are the same, so this chord CD is going to be congruent to this chord BE or AB, then their related arcs will also be the same. This arc will be congruent to that arc. So if AB's chord is congruent to CD's chord, then the arcs that relate it to them are also congruent. And if AB's arc is congruent to CD's arc, then the chords related to them will also be congruent. Now notice in all these theorems it says within a circle or congruent circles. So in other words, if we had two circles and we said this arc is congruent to this arc, then their central angles and those chords are congruent, then their central angles would be congruent and the related arcs would be congruent. Okay? So doesn't matter if they're in the same circle, as long as their central angles are the same, then the chords and arcs will be the same, or vice versa. Okay? All right, problem number 1 down below. Use the diagram at the right. Suppose that circle O is congruent to circle P, and that angle OBC is congruent to angle PDF. How can you show that angle O is congruent to angle P? From this, what else can you conclude? All right. So circle or complete the flowchart below to explain your conclusion. So we know that circle O is congruent to circle P. So OB is a radius, and all of the radiuses for all of these circles are going to be congruent to each other. So since our circles are the same, then all the radiuses on all the circles would be the same. So OB would be the same as OC, which would be the same as PD, which would be the same as PF. Okay? And then congruent circles have congruent radiuses. That's our reasoning behind that part of the flowchart. And from there, we can conclude that B and C are going to be congruent. Okay? Angle B and angle C. And that angle D and angle F are going to be congruent. Okay? And this is because of isosceles triangle theorem. All right, so if we have two congruent sides for our triangles in here, okay, so there's our triangle. These are our two congruent sides. Then the angles opposite of the congruent sides will also be congruent. Okay. Then we know that angle B is congruent to angle D. Okay. This was our given. That's right here. All right. And then together we could do the transitive property. And since D is the same as F, this part, and D is the same as B, okay, oh, I'm sorry, C is the same as F and D is the same as B, then we could put C and F together, okay? So we know that B and D are the same, so we can put the D over here, and then C is already over here, so C and F are the same by transitive property, okay? All right, and then we got C and F are the same. And we have all the matching sides are the same. So we know that the triangles are going to be the same. So triangle BCO will be congruent to triangle DFP. That's by angle, angle, side. Okay. Let's see. So we have this set of angles, and then either set of these sides we feel like from here. All right. So now that we have them the same, okay, then we can say that angle O is congruent to angle P. That's the corresponding parts of congruent triangles are going to be congruent. Okay. And then since the central angles are the same, then we can definitely say that the arcs should be similar. So BC's arc should be the same as DF's arc. And BC's chord should be the same as the chord DF. And that's from theorem 12-4 and theorem 12-5. Okay, so first up, what were we asked to do? So how can we show that angle O and P are the same? Well, we have to show that they have congruent triangles first, okay? And then we can prove that central angles are the same. And then once we have central angles the same, we can prove, from this, what else can you conclude? We can prove that the arcs and the chords are also the same. All right, let's flip it over and take a look at page 3. So we have theorem 12-7 in its converse, and then we also have theorems 12-8, 12-9, and 12-10. So theorem 12-7 says, within a circle or in congruent circles, chords equidistant from the center of the, or centers are congruent. So here's the center of our circle, and then here's two distances that measure the distance from the center to the chord. Notice when we measure the shortest distance, we have a right angle there, so it's going to form perpendiculars to show us the distance. Okay. All right, and this is saying that if those two chords are the same distances away from the center, then the chord should be equidistant. So if OE is the same distance as OF, then AB will be congruent to CD. So this says OE is equal to OF, then we would have AB is congruent to CD. And then the converse says the same thing. If the chords are equal and are congruent to each other or have equal length, then they're going to be equidistant from the center. So if AB chord is congruent to angle CD, or chord CD, then OE is going to be the same as OF in this case. Okay, so the distances the chords away from the center should also be congruent. All right, theorem 12-8, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Okay, so if AB is a diameter, that's this guy, it goes through the center, so he's a special chord that goes through the center, and it breaks, is perpendicular to another chord, so here's our other chord, CD, and they form a right angle, then it's going to bisect that guy perfectly. So this side and this side should be congruent. Okay, and the arcs that are split here, these minor arcs, will also be congruent. All right, so if AB is a diameter and AB is congruent to CD, another chord, then CE is going to be congruent to DE, the other half of the chord, and arc CA will be congruent to arc DA, the other half of the arc that's formed by the total arc CD. All right, 12-9. In a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular to the chord. Okay, so it's saying, hey, if I bisect, it's kind of like the converse of the other one. So if I split this chord in half with a diameter, then I'm going to have perpendicular here. All right, so if AB is perpendicular to CD, then AB contains the center of O. So this guy had to have been the diameter. All right, so in a circle, the perpendicular bisector of a chord contains the center of the circle. So that perpendicular bisector is going to be the diameter. Problem number 2, find the length of a chord. So what is the value of X? Justify your answer. So what is the measure of each chord? The measure of each chord is 36. Okay. You might write something like this. The length of one chord is shown as 36. Let's put shown down here. Is shown as 36. And the other has 18 for 2 segments. It's broken into 18 for both halves. So it is also 36. Okay. All right, circle the reason why the chords are congruent. So these chords are going to be congruent. They have equal measures. Okay. So if they're equal measure, they're congruent. So this one's 36. That's equal to this 36 for their measure. So therefore, they're congruent. Circle the theorem that you would use to find the value of X. Okay. So we're going to use theorem, or the converse of theorem 12-7. Okay. Which says that if two chords are congruent, then they're equal distance from the center of the circle. Okay, so that means since those chords are congruent, then these guys need to be equidistant. So this 16 should be the same as this 16. So circle the distances from the center to the chords. They're going to be 16. Therefore, the value of x should also be 16. All right, let's flip it over and check out our last page. Problem 3, using diameters and chords. So the diagram shows the tracing of a quarter. What is its radius? Okay, so underline the correct word to complete each sentence, and then we're going to do each step. So we're going to go through and fill this part in, and then I'm going to flip to the other page and show it so that I can use the tools on the smartboard a little easier. So first we're going to draw 2 chords. It's very difficult to draw a tangent to make a line only cross the circle once. Okay, next we're going to construct 2 perpendicular bisectors for each of those chords. Okay, so one perpendicular bisector for each chord, so 2 total. And then we're going to label the intersection where they cross C. This is going to be our center of our circle. And then we can measure out a radius. And the radius is going to be about something. So we'll figure out what that is in a second. All right, so let's flip it over and look at the circle. Okay, so you should be drawing on yours. So I'm going to take my ruler and draw 1 chord in. Okay. Now, they don't tell you this, but you cannot draw your chords parallel to each other or you won't get good results from this. Okay. So I have to turn my ruler a little sideways and then I'll draw another chord down here. All right, so now we have to make perpendicular bisectors, so we can move the ruler out of the way and grab this tool. To make a perpendicular bisector, remember you just open up your compass so that's more than halfway. Okay, and then we make marks here and here. And then we go to the other side of our segment and we do the same thing. We make marks here and here. All right, when we're done, we can then take our straight edge, put it on one of these intersections of our 2 arcs, and draw through the middle of our circle here. So let's see, we'll do this part in blue. And we get that. All right, so there's 1 perpendicular bisector. Now we have to do a perpendicular bisector for the other arc. So same thing as before. Okay, we put the pointy end on the intersection. And then I'm going to do this one in green here. All right, so we open it up to more than halfway. And we'll make an arc here. And we move it, oops, around to the other side of the line and make our other arc. And now we take the pointy end and put it on this side. And draw an arc so we can get our intersection. So there's 1 intersection. And then we spin it around here and get the other intersection. All right, so now we're going to take our straight edge one more time, line it up here, and draw this one in. So here's our other perpendicular bisector. Oops. Our other perpendicular bisector. Still not drawing well. Let's try it on the other side of the ruler here. All right, so our other perpendicular bisector. There we go. All right, so now these arcs are going to intersect at the center of the circle. So where they crossed will be our center. And then we can measure a couple different radius here, which one we feel like. So we could measure from the center to here. We could measure from the center to here, that's a radius, or center to here, or center to here. And when you measure yours, because yours is still drawn to scale, you should get about 12 millimeters. Okay. All right, so finding the measure in a circle. So in finding y, how does the auxiliary of BA make the problem simpler to solve? So BA is a hypotenuse of a right triangle. So BA is here, and that's going to be the hypotenuse of a right triangle because we have a right angle here where our line is the shortest distance to intersect our chord, and we know that's a right angle because we have it split into 11 on each side. Okay, so since BA is the hypotenuse of a right triangle, that's our first question mark. So you can use the Pythagorean theorem to solve for y. All right, so we know 11 in this triangle right here. This right triangle, we're missing y, but we know that this radius is also 15 right here. So we can find the measure of that missing side of our right triangle. All right, lesson check here. So this is a vocabulary one. Is a radius a chord? Is a diameter a chord? Explain your answers. So circle the names or figures that have 2 endpoints on a circle, and underline the names or figures that have only 1 endpoint on a circle. So a chord has 2 endpoints on the circle. A diameter is a special chord. It's the longest one for every circle. Radius has only 1 endpoint on a circle. And array and segment have nothing to do with circles at all there, so we can't do either one. All right, so is a radius a chord? This should be no. Is a diameter a chord? This is, of course, yes. It's the largest chord possible. And it says explain what's going on. So a radius has only 1 endpoint on the circle, so it's not a chord. But the diameter has 2. Okay, so if we draw a circle, a radius has only 1 endpoint on the circle, whereas a chord is supposed to have 2, and a diameter is a special chord that has 2 endpoints on the circle, but also goes through the center. All right, so this concludes our notes for this section. We still have words that we should understand. What is a circle? We should be getting pretty good at chords, and then we've known radius and diameter for many years. So rate how well you can use chords to find measures. And once again, if you're not in here, then you should really go back and watch this video again. You're going to see lots of stuff about this as we move forward in the chapter.